which is the time constant of this circuit, is 2 Henry divided by what? You can figure out this with the Norton equivalent if you want to. Okay, you can replace this with the Norton equivalent, and then you will finally get something that looks something like this. What is this resistor over here that you think it should be? Not 2, right? I do it two times, right? 1 ohm, right? This should be 1 ohm because the first time I replace it with the Norton, I get 1 and 1 over here, right? I get 2 ohm and 2 ohm over here. I get this circuit, so this in parallel give me 1, right? Give me 1 ohm. So L is 2, R is 1. The time constant of this circuit must be 1 over 2. Okay, this is the time constant of this circuit. Then I write down my general solution of IT. IT must be something of this form. Okay, that that there's no current through this thing in the beginning. So if I write it out in full, it would be something like this: e to the minus t over tau plus is. Okay, this is the general solution. I of 0 is equal to 0. I of s, what should I of s be? I of s should be the current through this system at t equal to infinity, right? If I look at this one, at t equal to infinity, what is I of t? It's equal to when t goes to infinity. If you just look at this circuit alone, I of t is just equal to Ix, which is 1m, right? So this must be just 1m. So without having to figure out what this current source is, you know that this must be just 1m. Because this will be the current that goes through this inductor. This Thevenin equivalent, Norton equivalent should be just 1m. Is it Norton or Thevenin? Norton equivalent should be just 1m, okay? That should be just 1m. So this must be 1m, this must be 0. So the solution must look something like this, plus 1. So this is how I of t would look like, okay? Okay? Does everybody get it? How I get this solution? Any questions on how to get that solution? Yes?
How do you get tau equals 1 half? And it should keep the whole one.
Tau is not, tau is equal to, L is equal to 2. R is equal to 1. So you're correct. It should be 2 over 1. It's 2. Okay, so tau is equal to 2. And then this should be equal to minus 0.5 t plus 1. Okay, thank you for pointing that out. So let's see. I have some time left. Let's do example 317. It's a little bit trickier. Okay, example 317. If you have no questions regarding this. I think I can erase this one. So let's do example 317. Okay, and this is a tricky example. I think the textbook draw those switches wrongly. This is 2 Henry. This is 2 ohms, and there's a current IT going through this inductor, okay, and there's a VT across this thing. This is 2 ohms, this is 2 ohms, okay. So IT must be going downward. So what happens is that previously you actually have solved this problem before in the previous example. Previously what you did was that at 0 time you turn it over to the other side. Okay, so at 0 seconds you turn it to the other side, and then at 2 seconds you turn it back. You turn this switch back. So you are supposed to use the previous answer that you had. At 0 second you turn it in, and then find out what you actually had at 2 seconds, and then turn it back and use that as the initial condition. Okay? So that one I think I erased over there. The solution for the previous problem after we have turned it over was that IT was equal to 2e to the minus 0.5 t amperes. Okay, that was when you flick the switch at 0 time to the left. And then at 2 seconds you're going to flip it back. So I at 2 seconds is equal to 0.5 t. This is just 1 amp. Okay, at 2 seconds there's a current that flows through the inductor. Now you set up the second problem and find out with this initial condition what the solution is for what you have on the right hand side. Okay, and you say that IT, the general solution is I2 plus, this is just right after 2 seconds, minus IS e to the minus t over tau. The tau is the time constant plus IS. Okay, you can convert this into a Norton equivalent, right? And then solve this, but there's no need to do that. Just figure out what IS is at t equal to infinity. If I flip the switch back to the other side, what should IS be? That is the current that goes through the inductor at t equals to infinity. It will be 2 amperes, right? So without even finding the Norton equivalent, you can figure out that IS should be 2 amperes without having to do the work. Okay, because you know that the current asymptotes to 2 seconds. I forgot the fact that this should be t minus 2 over tau. Okay, because I shift everything to the right by 2 seconds. So I should actually replace that. So IS is equal to 2 amperes. And then I have everything solved. I know what the solution is. I know this number, which is this number. I know what this number is. I know what tau is. Tau is equal to, I think I made a mistake on that and somebody pointed that out to me. L over R is equal to 2, right? And then you plug in everything. And you can plot the solution now. So what happens in this case is that in this case, you have something like this, I of t. And then as a function of time, something very interesting happens. In the beginning of time, you actually at 0 time, beginning of time, the current was going through this inductor entirely. So if this is t is equal to 0, in the beginning of time there was 2 amps going through the inductor. Okay. Yes?
After you switch the switch over at t equals 2, should R change back to 2 amps? So shouldn't L be just 1? Or should it?
Let me see. If I switch it back, then my time constant changes actually. You're correct. My time constant changes. So this should be tau. Let me call it tau 1 over R, and it should be this L over R is equal to 1. Okay, you're correct. Thanks for pointing that out. My time constant changes. So this goes to a new time constant. Okay, tau 1. Thanks for pointing that out. So in the beginning of time, what happens is that you have this exponential decay. When you flip it over at t is equal to 0, you go through this exponential decay. And this exponential decay with a time constant of 2. Okay? At 2 seconds, then you change your mind and say, I don't like this configuration. Let me flip the switch the other way around, okay? Let me flip the switch the other way around. And then what you have is that you will have to switch over to this expression. For this expression, what happens when t goes to infinity? The homogeneous solution disappears. The only thing left you have is a particular solution. The particular solution in that case is 2. So it also asymptotes to 2. Okay, so this is also 2 amps. But now it actually asymptotes to that constant value with a different time constant. Power 1 equals to 1. Okay? So this is how this thing looks like.
At t equal to infinity, it goes to 2e minus 1.
Let me see. If t goes to infinity, this term disappears, right? So it becomes just is.
Oh, sorry.
And is is equal to 2, so it asymptotes to 2 as well.
I got zero.
Okay, asymptotes to 2, and then this is how the plot should look like. So if you get everything right, everything shape correct, then you should be able to do the exam. Okay, remember your tau 1, tau 2, L1, L2, R1, R2. You get them in the right place. Time constants, then you should be able to do the exam. Are there any questions? I have 1 minute left, I think. Yes?
Why do we use capital letter I?
Why do I use capital I?
Yeah. What do I know?
Oh, because this is a constant source. I don't know. The textbook uses a capital I. I just follow the textbook. I guess this means it's a constant. Maybe that's what the authors mean. Ask Professor Kudeki. Okay. Why he think a capital I? I guess it's a constant. I can use lowercase, then it might mean the function of time. I think in his textbook, any lowercase variable are functions of time. Any uppercase variables are functions.
No, you don't.